All right, everyone, we'll take a look at the questions we had for homework assigned last Thursday. Did our lab on Friday, of course. Today's the first opportunity we have to check over these questions. Page 215, number 1 to 6. Those of you who did these questions, any issues with 1 through 6? Yep. 6B. Okay, we'll take a look at number 6, the whole thing. Yep. 5. Any others? Okay, we got 4, 5, and 6. Going once, going twice. 4, 5, and 6 it is. Number 4 says the moon has a mass of 7.35 times 10 to the 22 kilograms and an equatorial radius of 1.74 times 10 to the 6. What does that mean, an equatorial radius? We know what radius means, right? So this is from the center of something to the outside, right? So what does equatorial radius mean there, Dustin? Yeah, it's the radius at the equator. So what we're saying here is that moons and planets, they're not quite spherical. They're not a perfect sphere. The radius is different depending upon where you are, where you're measuring the radius. At the equator for the moon, the radius is this, 1.74 times 10 to the 6. Now, the Earth's mass is 5.94, and its equatorial radius is 6.38 times 10 to the 6. So looks like the moon is pretty much as big as the Earth, right? 10 to the 6 meters. Well, it's the same order of magnitude, but this is still 4 times bigger than this, right? 3 or 4 times bigger. So clearly the Earth is still much, much bigger than the moon is. 4A says, what's the magnitude, calculate the magnitude of the gravitational force exerted by the moon on a 100 kilogram student standing on the moon's surface and on the Earth, or of the Earth on a 100 kilogram student standing on the Earth's surface. Okay, well, we learned here last week about Newton's law of universal gravitation. We said that there is a force of gravity that acts between every 2 objects with mass. There is a force of gravity that acts between you and your neighbor. There's a force of gravity that acts between Jazzy's apple and the Earth. There's a force of gravity that acts between the Earth and the sun. Every 2 objects with mass, no matter how small or how big they are, including this 100 kilogram student on the surface of the moon. Now, that force of gravity can be found by this equation, F is equal to m times g. But there's a problem in finding the force of gravity on the moon with this equation. What is it? It's a valid equation, but why am I not going to use it here? What about gravity? It's different. So if gravity is different, why does this equation become difficult to use? When you you say gravity is different. Specifically, what variable do you mean is different? Right, good. We use 9.81 for the surface of the Earth. Now, it varies a little bit depending upon where you are, but not a lot, right? It's dramatically different on the moon. If we knew little g for the moon, we could use this equation. We just don't know it. So let's not try to use this equation when there's a missing variable. But we can use this equation. That's the law of universal gravitation. That's applicable everywhere. It doesn't matter what the value of little g is because we don't need it in here. Now, we do need the value of big G, but we have that. It's the same everywhere in the universe, 6.67 times 10 to the minus 11. Now, mass 1. Mass 1 would be the 100 kilogram student, and mass 2 would be the mass of the moon, which is 7.35 times 10 to the 22 kilograms. Divide that by r squared. Make sure you use the right radius here, the radius of the moon. And make sure you square that entire number on the bottom there. What do you end up getting there? I'm going to guess somewhere around 160. 161.925. Thank you, Joe. And that's going to be Newton's, right? The force of gravity. Technically, we should round that to 3 digits, 162 Newtons. I guessed 160. It's pretty close. It wasn't because I did that calculation in my head. It's because I knew what the force of gravity acting on this guy on Earth would be, roughly. And on the moon, I know that it's about 1/6. So I estimated. It was close. Okay, let's get the force of gravity on the 100 kilogram astronaut on the Earth. We can use the same equation, G m1 m2 over r squared. Now, Technically, we could use F is equal to m times g here as well and assume that g is 9.81 meters per second squared. That would be okay here. I would accept that. But since we've got this equation out, might as well use it. Make sure you use the mass of the Earth here and the radius of the Earth. Do this one lightning fast in our heads. It's going to work out to be somewhere around 981. Is it? What's the number there? 978. So of course I didn't do that calculation in my head, right? How did I guess a number that was pretty close to the real value? I cheated a little bit, right? How did I cheat? Yeah. I just said 100 times 9.81, right? 981. Okay, close. All right, why are the values of Fg different in part A? Why is gravity more, dramatically more on the Earth than it is on the moon? Yeah, that's it. The Earth is so much heavier than the moon, right? It's about 100 times heavier. 100 times heavier. That's going to make gravity quite a bit more, right? Now, it doesn't make it 100 times more because the Earth is also bigger. But it makes it more, about 6 times more, right? Next question that you guys asked for was number 5. Mars has 2 moons, Deimos and Phobos, each named after an attendant of the Roman war of god Mars. Deimos has a mass of 2.38 times 10 to the 15, and its mean distance from Mars is 2.3 times 10 to the 7. Phobos has this mass and a different distance. Phobos is closer than Deimos. Without doing any calculations, predict which moon will exert a greater force on Mars. Anybody want to take a stab here? We're not talking about a guy standing on the surface of each of these moons. We're talking about the force between each of these moons and the planet Mars. Which ones will exert the bigger force? Mars and Deimos, or Mars and Phobos, which is closer, which is heavier and closer. If you want to experience the greatest possible force of gravity caused by the Earth, where do you need to be? On the surface of the Earth? Or up in space somewhere, a big distance away from the Earth? On the surface. So the closer you are to the object that's causing the field, the stronger the force of gravity is going to be. And the heavier you are, the stronger the force of gravity is going to be. So Phobos is heavier and it's closer. It's going to be a bigger force of gravity on Mars than is Deimos, right? Now we can check our prediction in question A here by calculating the magnitude of each of these. Not sure we need to go through the actual calculations. In both cases, it's going to be gm1m2 over r squared. Same value for both of them. m1, we'll say, is the mass of Mars in both cases. m2, well, that's the mass of Deimos and the mass of Phobos, depending upon which one you're doing. R, the radius of Deimos and the radius of Phobos. Plug them in. Okay, when you plug them in, I don't know what numbers you get, but it doesn't matter. We know that the force of gravity between Phobos and Mars is going to be bigger than the force of gravity between Deimos and Mars. Okay. Is that okay? Who asked for that question? Is that okay? Or do you need to go through the math there? Okay. So you're good there? Okay. And number 6, the last one that we needed to go over here. So suppose the equatorial radius of the Earth was the same as the Moon. It's not, but let's pretend that it was. But the Earth's mass remained the same. The Moon has an equatorial radius of 1.74, and the Earth's mass is this, and the radius is this. What's the force that the hypothetical Earth would exert on a 1 kilogram object at the surface? G is 6.67 times 10 to the minus 11. Now, the mass, let's say mass 1 is a kilogram, and mass 2 is going to be the mass of the Earth. What's the value for r there? It's the radius, right, from the center of the Earth to the surface of the Earth. But we're pretending that the radius of the Earth is the same as the radius of the Moon. So we're not going to use this value of 6.38. We're going to use 1.74 times 10 to the 6. What do we get for that? 13,152. Dude, that's a pretty big force. 1.32 times 10 to the 4 newtons. Pretty big force. Okay, how does it compare to the actual force of gravity? Well, the actual force of gravity is also gm1m2 over r squared. But we use a different radius. All right, what do we get there? What do we get for that force? Somebody's got to have this one as well. John, you got that? $978. Wow. Big difference, eh? I expected a difference. I honestly didn't expect that big of a difference. Why? Why is the force of gravity exerted on this 1 kilogram mass on the surface of the Earth much, much bigger if the Earth is the size of the Moon? It's the same mass as it always has, but it's the size of the Moon. Why? Yeah. Yeah. Two things come into play when determining the strength of gravity. One is how heavy this object is that's causing gravity, right? The Earth, the Moon. Well, the Earth dents the fabric of space-time more than the Moon dents the fabric of space-time. But if the radius of the Earth is much, much smaller, then that mass is more tightly packed, so it dents it even more. That makes sense? Okay. So the idea here is this. If you can pack a lot of mass into a big volume, well, that creates a lot of gravity. If you can pack a lot of mass into a smaller volume, it creates even more gravity. Smaller r, bigger F. Okay. We talked a little bit on Thursday about gravitational fields as well. We said, you saw these notes on Thursday, so nothing new here, I don't think. A field is a line of influence that surrounds something. We talked about when I hold this pen in my hand, there's a force of gravity acting on it right now, caused by the Earth. The dent in the fabric of space-time is influencing this pen. I let it go, it falls. It falls down toward the Earth. It follows the curvature of space-time. But if I take away this pen that follows the curvature of space-time, the dent in the fabric of space-time is still there. Gravity is still there, even though there's nothing being influenced by gravity. Gravity is still there. So how do we describe that? We can't talk about a force, because a force is a push or a pull. In order to have a force, you need something to cause it, that's the Earth, and you need something to experience it, that's the pen. But if we have just the Earth, the thing that causes it, even though there's no force, something is still there. Well, we call that a field. The field is the influence that surrounds something, not the push or the pull, but the potential influence that surrounds something. In order to have a field, all we need to have is a producer. In order to have a force, we need to have the producer and the experiencer, the thing that experiences it, the pen. Now, we talked about gravity as being a vector field. It has a direction. Does it influence this pen? Yes. Does it influence it in a particular direction? Yes. Every time I let this pen go, what happens to it? This is not a rocket science, right? No trick question here. What happens when I drop this pen? It falls. Every single time it falls downward. If the influence of gravity causes it to go in a particular direction, then it's got to be a vector field. The vector field would be an electric field, a magnetic field. A scalar field might be a light field. Does light influence us? Yes. Does it influence us in a particular direction? No. That's a scalar field. All right? Every mass, no matter how big or how small, will experience a force in the direction of the field. In fact, that's how we define the direction of the field. Gravitational field is downward because that's the way masses move when placed in the field. So let's draw a picture here first. This is the Earth. I'm drawing it as the Earth, but it could be any object with significant mass, the sun, the moon, whatever. Here's one gravitational field line. Here's another one. Here's another one. Call it a radial field. A radial field, the field lines radiate out around it. They point towards it. If I was to put an object, let's say a pen, right here, it would experience a force downward. If I was to put a pen right here, it would experience a force which way? This is downward. This is, which way is that force? Downward, right? Gravity is always downward. Do you think people are standing in Antarctica right now? Like kind of standing on their heads, like upside down? Down is toward the producer. Down is toward the Earth. So objects will always move downward in the direction of the field. All right, we got a couple equations that describe this all. The first one, the more complicated of the two, we're going to say G. G is the gravitational field strength. We're going to put absolute value signs around this because this equation isn't going to tell me the direction. That's okay. I don't need the direction. I know which way it points. Just like centripetal force always pointed toward the center of the circle, gravitational field always points downward toward the producer, toward what causes it. The equation looks familiar, eh? It's a lot like this one. It's a lot like that one, but it's not the same. Don't get it mixed up. The gravitational field, Gm over r squared. The other one? F over m. Now, this is what we call our producer equation. This is what we call our experiencer equation. When you have information about what causes the field, what produces the field, you'll use the first equation. When you have information, that would be the Earth, right? In many cases. When you have information about what feels the field, what experiences it, what's exposed to it, then you're going to use the second equation, the experiencer equation. We could, the pen's in my hand right now, about a meter above the Earth. We could find the field strength caused by the Earth at that point. We could find the field experienced by the pen at that point. It would be the same thing. Because, of course, what field does the pen experience? It's the field that's caused by the Earth. All right. So what do we got here for variables? Well, we know what G is. Constant. 6.67 times 10 to the minus 11. What's M stand for? Easy question, right? Easy question. What's M stand for? Mass. But what mass? What mass? The mass of the pen or the mass of the Earth? This is the producer equation. What causes gravity? The pen or the Earth? The Earth. So what mass are we going to use here? The Earth, the mass of the producer, whatever that happens to be, the mass of the producer. And r, be careful, r is not a radius. It's a distance from the center of the producer. Distance from the center of the producer. What's this F? We're talking about the experiencer equation, right? The pen experiences a force of gravity. It's the force of gravity felt by something. The force of gravity experienced by something. And m would be what? The mass of, let's use the Earth and the pen again as our example here. This would be the mass of what, Jazzy? Or heavy, I mean. Yeah, sorry. The pen. Yeah, the mass of the producer. Or sorry, experiencer, right? The mass of the experiencer. When should we use each equation? Listen, it doesn't matter which equation you use as long as it fits the givens that you have. If you have givens about whatever is causing the field, then go ahead and use the first equation. If you have givens about what experiences the field, the pen in this case, then use the second equation. What if you have information about both, the producer and the experiencer? You know all you need to know about the Earth. You know all you need to know about the pen. Which equation should you use? It doesn't matter. Use whichever one you want if you have information about both. Okay? Just make sure your givens fit, just like any other question we do. Now here's a bunch of masses of different planets and so on, and some radiuses of those. We'll have ourselves a little quiz on that tomorrow, so if you can memorize those for tomorrow. No quiz. You know what? No quiz on that tomorrow. 4.5, page 218. Calculate the magnitude of the gravitational acceleration. Wait a second. Acceleration of an object at the equator on the surface of the moon. The acceleration. We've been talking about gravitational field, right? Let's go back here for a second. This is the gravitational field, right? Let's look at the units for it. Newtons per kilograms. Okay, what's a Newton? Newton is mass times acceleration, right? So it's kilograms times meters per second squared divided by kilograms. Okay, kilograms cancel. Wait a second. So the units for gravitational field end up being the same as acceleration. It's a gravitational field that I experience right now, 9.81. The gravitational field is the acceleration due to gravity. So in this question, when they're asking us for the magnitude of the gravitational acceleration, they're really asking me for the magnitude of the gravitational field at the equator, on the surface of the moon and the surface of the Earth. Okay, let's find the field strength on the surface of the Earth. We don't know anything about this person on the surface. That's a big person, by the way. It's a really big person. We don't know anything about that person, though, other than she's really big. In fact, bigger than the moon. We do know something about the Earth, though. The gravitational field caused by the Earth on its surface can be found by the producer equation, because the Earth produces the field. 6.67 times 10 to the minus 11 times the mass of the Earth, which is 5.97 times 10 to the 24, divided by the radius of the Earth, which is on that sheet, 6.38 times 10 to the 6 meters. Listen, what do you think we should get when we do that calculation? Give me a guess right now before you punch into your calculators. What do you think we should get? Austin? Somewhere around 9.81, right? Because the field strength on the surface of the Earth, although it varies a little bit, is usually around that range of 9.81. Okay, let's punch it in and see what we get here. We end up getting 9.78. We can use units of newtons per kilogram or meters per second squared. Both of them work. We know that we've done this right. Okay, when we get a number that's that close to 9.81, we know we've done it right. All right, on the surface of the moon, GM. The mass of the moon, 7.35 times 10 to the 22. And the radius of the moon was 1.74 times 10 to the 6. Square that. I'm going to take a guess at this one as well, somewhere around 1.6. We get 1.62 newtons per kilogram or 1.62 meters per second squared. Okay. We knew it was going to be somewhere around there, about 1/6 of what it is on Earth. Now we want to find a ratio. What's a ratio? The ratio. How old are you guys? 16, 17? 16? Okay, so you guys are 16. Probably most of you guys are probably 16. Let's pretend for a second I'm 32. What's so funny? How old do you think I am? 42, what? I am 42. Yes. Let's pretend I'm 32. Easier math, exactly. Okay, what's the ratio of my age to your age? If I'm 32 and you're 16, what's the ratio? That's an easy question, right? What's the ratio of my age to your age? 2 to 1. How'd you get that? 32 divided by 16, right? We divided my age by your age, and we got 2. So the ratio is 2 to 1. Listen, if you want to find a ratio of the gravitational field caused by the Earth to the moon, then let's divide the two. 9.78 divided by 1.62 gives us around 6. I don't know what it is exactly. 6.04, so pretty close. 6.04, that means the ratio is 6.04 to 1. That makes sense? Okay, have a look at the 3 questions on page 218 now, please. See what you can do with those, and then we'll keep going after that. All right, let's take a look at our next example, our last one of the day. It says, what is the mass of a 60-kilogram student on Mars and the Earth? Oh, boy. What's the mass of a 60-kilogram student on Mars and the Earth? 60 kilograms. Simple as that, 60 kilograms. All right, what's the student's weight at the equator on the surface of Mars and the Earth? What's the student's weight on the surface of Mars and the equator? Okay, well, the weight is the force of gravity. So we want to find the force of gravity experienced by this student, this 60-kilogram student on the surface. Now, we got a couple of options here. Let's do the Earth first, okay? Okay, in the end, if we can do the Earth, we can do the moon, right? The gravitational field produced by the Earth is equal to gm over r squared. That's 6.67 times 10 to the minus 11. The mass of the Earth was 5.97 times 10 to the 24. And the radius of the Earth was 6.38 times 10 to the 6. And I think when we did that, I think we got 9.78, wasn't it? We did that a few minutes ago. John, 9.78 was it? 9.78 newtons per kilogram or 9.78 meters per second squared. All right, there's the field, Tom, caused by the Earth at that point, Ryan. The field caused by the Earth at that point. Now, let's find the force that's experienced by that student. The producer equation, the experiencer equation. Let's rearrange the experiencer equation. the mass of the student, the mass of the experiencer is 60 kilograms, and we multiply that by 9.78. Okay, that's the gravitational field strength, or the acceleration due to gravity. And what do we get there? It's going to be something like 585 or something like that? 586? What is it? 587 newtons. So we used the producer equation to get the field strength at that point. We used the experiencer equation to get the force at that point. Does that make sense? Now, what's our other option? What else could we have done to find the force of gravity or the weight of this person? I could have just done this. Wouldn't that have given me the weight, the force of gravity? If you combine this equation and this equation, what do you think you get? G times the mass of the producer over the radius squared divided by the force over the mass of the experiencer. Let's rearrange that. We end up getting gm1m2 over r squared. So we did it separately by using fields. We could have done it combined using the force equation. It doesn't matter. Okay, they all work together. Your homework for tonight. Questions on page 218 that you were working on a few minutes ago, and the questions on page 220.